Welcome, ladies and gentlemen. May I have your attention, please? Thank you. I don't know if you guys have seen, but the Twitter boards have been blowing up after we did our 3A recording. I don't know if you've seen on our YouTube channel too. The likes is just astronomical. The number of views, along with the number of subscribers, it just skyrocketed as a result of our recording class 3A. And so we're going to continue to record 3A. Also, there's been a little fan club started on Facebook. I don't know if you guys have seen some of those posts. Wanting more Ethan, the guest celebrity voice, Ethan. Give us more Ethan, give us what we want, give us more Ethan now, something like that. I don't know. And so we're going to go ahead and continue recording our 3A class because you guys did a great job last time. Okay, so at this time, raise your hand if you didn't get a red mark for today, the 1st of December. It's hard to believe we're already here. Great. We can generate inverse functions equation algebraically by using our 4-step process. And first, we rewrite with y equals instead of f of x equals. And then how do we get the inverse, right? How do we find the inverse of a function? Well, we invert the position of x and y in our equation. So in the most basic sense, an inverse relation inverts the position of x and y. So our first step then, after rewriting with y equals, would be to invert the position of x and y. So now, not y equals, but x equals. And not 3x plus 7, but 3y plus 7 all over 2. And so there, we've inverted the position of x and y, and now we're going to solve for the new y. So depending upon where that new y is, you'll use a different series of inverse operations. It looks like to me the best first step would be to multiply both sides by 2. That'll get rid of the fraction. Followed by a subtraction of 7 from both sides. And lastly, it looks like we can divide both sides by 3 to finish it out. Now, depending on how we rewrite this, you could break it up and make it look like slope-intercept form, or since my original was already a large fraction, I'll leave this as a large fraction. My final of the 4-step process then would be rewrite this y as f inverse of x in accordance with the appropriate notation for inverse functions. So my final step, I'm going to go ahead and call this f inverse of x is given by 2x minus 7 all over 3. At this time, I'd ask that you go ahead and check your paper and raise your hand if you already had f inverse is given by 2x minus 7 all over 3. Good, you guys. You could also have 2/3 x minus 7/3, and that would be entirely appropriate. And now we want to go ahead and see how these would compare graphically. So how do a function f and its inverse, f inverse, compare graphically, right? How do they compare graphically? Mason and Nathan?
Would there be a reflection over the line y equals x?
A reflection over the line y equals x? Let's see. So I'm going to go ahead and use the emulator there, and we'll graph the original and its inverse on the same xy coordinate plane and see how they compare graphically. And we'll see how Nathan's description compares. And so once again, my original was f of x equals 3x plus 7 over 2. I'll go ahead and enter that in my y1. So quantity, 3x plus 7. Closed quantity all over 2. We'll enter my inverse function. My inverse function was 2x minus 7. So I'll do quantity, 2x minus 7. Closed quantity all over 3. And then, Nathan, you said that was going to be a reflection over what line?
Y equals x.
Y equals x, so we'll enter our third function, y sub 3, as the identity function x. I'll go ahead and take a screenshot of this, and then I want to do not just zoom 6, but zoom square to counteract for the fact that the viewing window is actually rectangular. If I do zoom square, it'll counteract for that rectangular shape. So I'm going to do z square, and watch what happens. So here comes my original function f in blue. Here comes the inverse in red. And then the mirror image line that Nathan suggested, y equals x. If they are, it should cut it right down the middle. Just like Forrest Gump, when he's leaning against Bubba, right, in the rain in the jungles of Vietnam, and Bubba says, you lean against me, I'm going to lean right back. That way we don't have to sleep in the mud. Because they're going to split the shrimping piston right down the middle. 50-50. All right, guys. So we've gone ahead and seen that Nathan's description is exactly correct. It's split down the middle, 50-50. They're mirror images of one another when reflected about the line y equals x, and we can state that as our description. So a function f and its inverse, f inverse of x, are reflections of one another about the line y equals x. Awesome. So we'll go ahead and come back to that table later. We're going to use that to generate our first content objective. Today we're going to apply the compound interest formula known as continuously compounding interest. Continuously compounding interest. We're going to introduce the number so famous it gets its own letter. And we're going to define and evaluate logarithms. So a great big day, and we got to get started right away. So let's go ahead and get going right away. If you could take out your assignment number 1, please, and give yourself credit for those who completed out of 16 in pencil. Divide, enter, multiply by 4. If you did your reading questions, you're eligible for a 5th point. If you didn't do your reading questions, your max into the camera score will be out of 4. And I'll go ahead and pause the recording while we do our homework check for answers. Thank you. Today we're going to investigate what happens to our regular compound interest formula that we investigated last unit, right? When the number of compoundings over the course of a given time period increases. And so we've already done calculations like how much money remains after a principal investment, right, at a given interest rate if it's compounded quarterly versus semi-annually versus monthly. Let's go ahead and consider what happens if we continue to increase those number of compoundings, and not just monthly, but daily, or by the hour, or by the second, right? What's going to happen to the amount of money at the end of a particular investment period? Well, to investigate this, we can use our graphing calculator and take a look at our chart here. Suppose, to simplify matters, we let our principal investment be $1. We let our interest rate be 100%. As a decimal, that of course will just be 1 to go along with our time period of 1 year. So we're going to use 1 for everything, except we're going to let n, the number of compoundings that occur within a given year, change, right? We're going to let that vary. That's going to be our x variable. And so in our graphing calculator, that n is going to be our independent variable x, and we'll enter that in our y equals many. First, though, I want you to share with the class the number of compoundings for n, right? What will n equal if we compound annually? I'll do that 1 versus semi-annually would be 2 times a year. What would quarterly be? Luke? 4. Thank you. Be ready to share. What would monthly be? Monthly. Isaiah? 12. Thank you. What would daily be then? Daily. Mackenzie?
165.
Thank you. What would hourly be? Right? What would hourly be? Don? 8,760. Awesome. And lastly, what would by the minute be? How many compoundings n would occur over the course of a single year if we compounded every minute, right? If we compounded every minute, what would you get for that? Claire?
125.
Awesome, thank you. So let's go ahead and rewrite my equation. Instead of a equals, let's use my graphing calculator menu, and I'll do y sub 1 equals. We'll do a principal investment fee of $1 times the quantity 1 plus interest rate of 100% would be as a decimal 1 over, and then we'll let my n variable be my x variable in my graphing calculator, and that's all raised to the 1 year times x, and so we'll raise that to the x power. So everybody, let's go to our graphing calculator, and in our graphing calculator menu we'll clear out our function and inverse function from the Bellwork, and we'll enter our new function y1 equals 1 times quantity 1 plus 1 over x, closed quantity, all to the 1x power. Take a minute and make sure that you have your equation entered correctly. Now we're going to go ahead and we're going to use my table. We're going to use my table to figure out what amount A exists at the end of a year, depending upon my number of compoundings. And so we want those x values to change. In order to do this, I can go to my table set, that is second window. Everybody go to your table set, second window, and we're going to change my independent variable to ask. So I'm going to toggle down with my cursor using the arrow keys on the arrow keypad and highlight ask and press enter so that now I can ask the calculator for given x values as opposed to scrolling up with the dependent, right? I'm sorry, scrolling up or down with the auto. So everybody on ask? All right, so let's go ahead and go to my table now. Again, that second graph to go to my table. And I'm going to enter my x values. 1, 2, 4, 12, 365. If it's not letting you enter x values, it means you didn't set your table correctly. So go to second window table set and pick independent ask. And that'll allow you to ask the calculator what a given independent variable value produces. So once again, let's go ahead and enter our x values there and then copy down the corresponding amount to y. So as the number of compoundings increases, what's happening to my amount at the end of the investment? Well, it appears as though it's increasing as well. However, is it increasing to infinity as I continue to let the number of times? Is it going towards infinity? No, it's not going towards infinity. It appears as though it's kind of, I don't know, leveling off at some number that's around 2.712818. I don't know. Let's see. So let's go ahead and write down those values. It looks like from my table, we get at the end of a year, if we only compounded once, we got $2 versus $2.25. If we compounded semi-annually, $2.44. If we compounded quarterly, $2.61. If we compounded monthly, $2.71. If we compounded daily, hourly would get us to $2.72. And by the minute, every single minute, if we compounded interest again based on the previous minute's amount, it looks like it'll only get us a little bit more. So that would be 2.71828. And now we see that this is converging on some number that's so important, it gets its very own letter. Yes, that's right. I would like to introduce you to Euler's number. So Euler's number is so special, it gets its own letter, E. The number E is about 2.7182818450452 dot dot dot. It goes on forever. And while it looks like it's going to fall into a repeating pattern initially, you guys see that? It looks like it just might fall into a repeating pattern. Then it goes crazy. It is in fact irrational. Just like pi, a transcendental number that has a decimal, never stops and never falls into a repeating pattern. It's irrational. Euler's number shows up in a variety of real-world applications. Anytime we're dealing with continuous growth or decay, it's an opportunity to use Euler's number, right? Euler's number E. And while Mr. Akers, Mr. Notsky, and Mr. Marks are only requiring that their students memorize the first 20 digits after the decimal place, I think we're hardcore, right? And we can go the first 30 decimal places. And so for us, on the first quiz, we'll go ahead and write down the first 30 digits of E, because that's how we roll, right? We don't need 20. So easy. We're going to go 30, okay? 30. And so that's not an actual quiz question. It's not an actual quiz question. I mean, obviously, I think you should still know them by heart. But E is a famous number, and it's used here to represent continuous growth or continuous decay. So anytime you see those words continuously, right, growing continuously or decaying continuously, then we're going to be authorized to use this new formula. It generally comes from compound interest, right, in this case, but it can be applied to radioactive isotopes for decay. It can be applied to population growth, right? For growth. And so anytime we're dealing with continuous growth or decay, we can use the number E. Let's go ahead and use this formula and compare it with our compound interest formula from before. Let's suppose that Mona invested $8,218.16 in a zero coupon bond paying 4.5% APR compounded semi-annually. After 25 years, she'd have about $25,000. Let's compare that with continuously compounding interest formula. The same principal investment, the same term of the investment, 25 years, but now let's use the formula A equals P times E to the RT. So anytime we have the words continuously, continuous growth or continuous decay, then we're authorized to use this formula. So let's go ahead and evaluate this formula. A equals principal investment P times E, the number E, about 2.71828 raised to the RT. For the specific principal investment, $8,218.16 times E to the, and my interest rate as a decimal, 4.5% is going to be 0.045, and then times my term of the investment was 25 years. So everybody on our home screen will evaluate this. The number E, right, the number E can be found either by doing second division sign as the number E, or we can do E to the by pressing second ln, and ln is short for natural log. We'll see that in the next two sections. Right here, second ln is E to the, and that'll spit up a caret. So let's go ahead and see if we can evaluate this. 8218, bless you, 0.16 times the number E is right there. Second division symbol is the number E. It's a number, not a variable. It's a number. To the, and I'll go ahead and in the exponent, I want to put 0.045 times 25, and that's all up in my exponent. So once again, we're going to do the number E is second division or second ln, and then I'll already put up the caret, and then we'll evaluate it. And did I get my decimal place right? It looks like about $25,313. And 71 cents. So when compounded continuously, would Mona have made more or less money if she were compounding continuously? Would she have made more or less? Ben C?
More.
More by how much?
Looks like $313.71.
Yeah, so it wasn't right. It wasn't an infinite number, but it was certainly more than if she was just compounding semi-annually. Good. So this formula, while in this case it was specifically used for money and interest, shows up when we're dealing with bacteria and population growth or decay, carbon dating, right? Radioactive decay, such as the case with our next example. Let's go ahead and take a look at a growth and decay problem. This is a radioactive substance again, much like we did with strontium-90 during last class period. Suppose that the amount L of a certain substance remaining after T years decreases according to the formula L equals B times E to the negative 0.0001 times T, where B is my initial amount of that radioactive substance, L is the amount left in grams, and T is the time in years. If 2,000 grams are left after 6,000 years, then how many grams were present initially? And so this is a classic example of how the number E is used for radioactive decay. We need to find B, which is the initial amount present. And so when T equals 6,000 years, then L was the 2,000 grams that were left. And so 2,000 grams are left after 6,000 years. Let's go ahead and figure out what B is. My original B would be my initial value, right, for my exponential form. How much did we originally start off with? All right, guys, so let's go ahead and rewrite my original. L equals B times E to the negative 0.0001 T, but let's substitute in our values. So we'll start out with our regular. L equals B times E to the negative 0.0001t, but rewrite it, plugging in 2000 for L, don't know for B, e to the, bless you, and t is 2,000, no, 6,000. So how do we do? We rewrite our original, but everywhere we see an L, we put 2,000 for the amount left after 6,000 years for t, and then we're going to solve for B. All right. So if we try to solve for B, remember e is just a number. What operation is going on between B and that exponential on the right? Well, right here, there's an invisible multiplication. So I could undo that multiplication by division and solve for B in one fell swoop. So that's what I'm going to do. I'm going to divide both sides by e to the negative 0.0001 times 6,000. And that'll get B alone. So I'm going to go ahead and take my 2,000 and divide it by e to the negative 0.0001 times 6,000. And see what we get. Whoa! We don't want that. Good heavens. Guess I can't do that. Well, I can do this. So let's go ahead and try. Watch your parentheses, you guys. I'm going to do 2,000 divided by e to the, and this time I am going to do second element because it'll spit up a raised to the and parentheses, so I know all that's going to be in my exponent. So what's my exponent? Negative 0.0001 times 6,000, all up in the exponent. When I press enter, should we get more, right? More or less grams than 2,000? We're going to be starting out with more or less grams than 2,000. So if we found our correct initial value, right, would we start out with more or less than 2,000? Ethan?
More?
More, right? Absolutely. We would be starting out with more than 2,000 if it decayed to equal 2,000 after 6,000 years. Nice job. Thank you. And so it looks like my initial grams present is about 3,644.238 grams. And that's what we'll go ahead and indicate as my initial value. Awesome. We want PDFable, so I think I'm going to put that here too. What questions do you have about our radioactive decay problem? Okay, so keyword continuously, that's what's going to authorize the use of our Euler's number equation, our continuously compounding interest formula, which shows up as radioactive decay or population growth. All right, for the second content objective today, we're going to define and evaluate logarithms. And the good news is that logarithms are just exponents in disguise, right? We're going to be learning about logarithms, which is a brand new concept for you, except it's based on a previous concept that you guys are very familiar with, and that's exponents. So a logarithm is just an exponent. It's old product in new packaging, and we're going to figure out what that packaging, that notation is today together. So on the Bellwork, we found an inverse of that function, f of x equals 3x plus 7 over 2. Now we're dealing with exponential functions, right? Not linear functions, and it turns out that the inverse of an exponential function is what we call a logarithmic function. And so the inverse of an exponential function is a logarithmic function. We're going to be able to rewrite exponential form as a logarithmic form. And the good news is that to evaluate logarithms, we just need to know our knowledge of powers, because a logarithm is just an exponent. So let's go ahead and get cracking. So let's consider the graph of an original function f of x equals 3 to the x. Back in middle school, we created graphs on the xy coordinate plane by choosing x values, evaluating my function rule, and then plotting the points x comma y on the coordinate plane and connecting them. Let's do the same thing to generate a basic picture for f of x equals 3 to the x. Let's go ahead and choose some convenient x values, like -2, -1, 0, 1, 2. We'll plug those into my function rule for x and evaluate to get the corresponding output values, function values, y values. So let's plug in -2 for x. 3 to the -2 is 1 over 3 to the +2. That's 1 over 3 squared is 1/9. 3 to the -1 would be 1 over 3 to the first. That would be 1/3. 3 to the 0 would be 1. 3 to the first is 3. And 3 to the second is 9. After you complete your table of values, let's carefully plot those on the xy coordinate plane. I'm going to use blue for f of x to match this color on the smartboard. So -2, 1/9 be right there. -1, 1/3 be right here. 0, 1, 1, 3, and 2, 9. Wow. This is very, very steep as I move along this function from left to right. This is a classic exponential growth function. My base b is bigger than 1. In fact, a lot bigger than 1. It's 3. And look what happens. Slowly increasing, and then once I get to the right, wow! It gets very steep very quickly, and that's characteristic of an exponential growth model. In the most basic sense, an inverse function inverts x and y in my original equation. And so if I wanted to consider what the graph of an inverse function is, I could get ordered pairs by inverting my x and y in that original function. So if y equals 3 to the x was my original, then x would equal x would equal 3 to the y in the inverse relation. How could I get points on the relation x equals 3 to the y? Well, I could invert the xy coordinate pairs from my original, right? Invert the position of x and y. And so on the original, I had -2 paired with 1/9. Guess what point's going to be on the inverse? Well, 1/9, -2. The original point, -1, 1/3, is going to correspond to the new point, 1/3, -1. Go ahead and complete the inversion for each of those xy coordinate pairs and carefully plot them on our xy axis. Awesome, look at this. So not only are an exponential function and its inverse mirror images of one another about the line y equals x, right? We can see that. We can gain coordinate pairs by inverting x comma y in my original to get new xy pairs in my inverse functions. I'm going to go ahead and add in that diagonal line y equals x that Nathan shared earlier, because visually, right, that's a good indication of how they compare and a reminder. Okay, so right now I have an equation. X equals 3y is the inverse of y equals 3 to the x. But I don't know how to write that, solve for y, f inverse of x. And so on the next page, we'll now get a definition for a logarithmic function. So x equals log base b of a, if and only if b to the x equals a. The function f of x equals log base b of x is the inverse of the original function, y equals b to the x. And so we can invert the position of x and y, and then rewrite it as a logarithm, y equals log base b of x. It's called the logarithmic function with base b, and it's the inverse of the exponential function g of x equals b to the x. So let's go back to the last page now. We're going to rewrite my inverse function, x equals b to the y, as a logarithm. Y is going to equal log base b of x. In this case, what was my base in the exponential? 3. Therefore, my f inverse in red is going to be given by log base 3 of x. And so f inverse of x equals log base 3 of x is the inverse function of y equals 3 to the x. The base in my exponential function is the base in my logarithmic function. To show the base in a logarithm, however, I write it as a little subscript. All right, I write this as a little subscript down here. A logarithm is an exponent. And so if this logarithm is an exponent, what is the exponent? The exponent is y. Take a look at my expression rewritten in exponential form. My exponent was y. Right? My exponent was a y. And so base to the exponent equals input, 3 to the y equals x, and that's exactly what we saw, 3 to the y equals x. And we're going to practice with this form in just a minute. 5 cubed equals 125 can be rewritten in logarithmic form because a logarithm is just an exponent. Okay, the base in a logarithm corresponds exactly to the base in my exponential form. Everybody, 5 cubed equals 125 means that log base 5 of 125 equals 3. What? The base of my logarithm, right, is the same as the base of my exponential form, and the logarithm overall is an exponent. And so my exponent in that power statement was 3. My logarithm overall equals 3, and base to the exponent equals input. 5 to the third equals 125. Take a look at the second one. The base in my power statement, 16, is the subscript base in my logarithmic statement. Log base 16 of 4 equals the exponent. The exponent was 1/2 in my power, so the overall log equals 1/2. We can rewrite this in power form. 16 to the 1/2 equals 4 because the square root of 16 is 4. Lastly, the base in my original power statement, in this case a, is the base of my logarithm. A of the input b equals the exponent u. Not only can we rewrite exponential form as a logarithm, we can also start at a logarithm and rewrite an exponential form. And this way is even easier, right? Log base 3 of 9 equals 2 because base to the exponent equals input. What's the base? 3. What's the exponent? 2. What's the input? 9. Guess what? Log base 3 of 9 equals 2 because 3 to the second equals 9. It's just old information in a new package. It's a logarithmic statement as opposed to an exponential statement. Base to the exponent equals input. Let's do another one. It can be useful to think of that decimal 0.04 as a fraction. That's 4 100ths, which is equivalent to 1/25. So let's rewrite an exponential form. Base 5 to the exponent -2 equals 0.04, which is 1/25. What? 5 to the -2 is the same as 1 over 5 to the +2. That's 1 over 5 squared is 1/25. Matab?
Could you just write 0.04? Do you have to do it?
No, you can do 0.04, that's fine. I was just trying to see how we could make the connection there with power. Go ahead and write the last statement as an exponential form. We'll be ready to share with the class when I call on you. Base to the exponent equals input. What would that look like for the last one? And what would that look like for the last one? Maggie?
7 to the 0 power equals 1.
Raise your hand if you have the same as Maggie. 7 to the 0 equals 1 is absolutely correct. Good job. Base to the exponent equals input. Base to the exponent equals input. All right. Now we're going to go ahead and get our super duper fadeaway shapes, right, to determine what the exponent is in each of these power statements. Remember, a logarithm is just an exponent. It's an exponent in disguise. And so when you go to evaluate a logarithm exactly without a calculator, you're just asking yourself an exponent question. What exponent must my base be raised to equal the input 32? What? What exponent must the base be raised to? So I'm asking myself 2 to the what exponent equals 32. That's what log base 2 of 32 is asking me. It's an exponent question. 2 to the what exponent equals 32. Oh, I know that from my powers half sheet, which you'll be allowed to use on this unit's quiz and test, just like last unit's testing quiz. So 2 to the what exponent equals 32. Oh, 2 to the fifth equals 32. So log base 2 of 32 is 5. because that's the exponent that my base 2 must be raised to equal 32. Let's try another. Base 3 to the what exponent equals 27. Go ahead and get your power attached sheet. Log base 3 of 27 is an exponent question. It's saying what exponent must base 3 be raised to equal 27? Everybody find it. So what must 3 be raised to equal 27? Mason?
3.
Absolutely. Guess what? Log base 3 of 27 is 3. Good, thank you. 10 to the what exponent equals 10? Well, 10 to the first power equals 10. A logarithm is just an exponent question in disguise. We can even get trickier. 9 to the what exponent equals 3. What? That's not on my half sheet. Well, it kind of is, right? 9 to the what exponent equals 3? Well, the square root of 9 is 3, and as a fraction, right, a square root as a fraction 1/2, right? 9 to the 1/2 power equals 3. In the same way, then, the cube root of 27 is 3, so 27 to the 1/3 equals 3. Again, you could think of this decimal input, 0.0001, as a fraction. That might help you with your exponent determination. So this looks like 1, 2, 3, so that's 1/10,000. So 10 to the what exponent equals 1/10,000? Well, I need a negative exponent to make the reciprocal, to make a fraction, and then raise to the 1, 2, 3, 4th power, because 4 zeros are behind it. So put it all together, and we get -4. That's pretty sweet. Go ahead and complete 7 and 8 and 9 with your partner. It's okay to talk. I want you to figure out what exponent the base must be raised to equal the given input, and that's your answer. A logarithm is just an exponent question in disguise. So go ahead and do those with your partner and be ready to share. 7, 8, 9, 10 with your partner.
Would that just be 1/9? No, it's 1/2. Are you listening? Do you know what you're doing?
If you guys want to check, just go ahead and on your note sheet, click the shape, right? Click the shape so it fades away and shows you what the answer is behind it.
It works for mine. It does. Did you get for 9?
Jimmy, you want to go ahead? Go ahead. 7.
That would be negative. Okay. So 0.5 equals 0.5 times 0.5 times 0.5 times 0.5. Okay, so it equals like 0.016.
Okay, thanks to those of you who are selected to come up and click the shape reveal. You had the correct answer for each of these exponent questions. Remember, a logarithm is just an exponent question in disguise. 9 to the what exponent equals 81? Well, 9 to the second equals 81. Raise your hand if you had number 7 right. Good. Raise your hand if you had number 8 right. That's a square root, so 1/2 would be the exponent. Good job. Thanks, hands down. Number 9 is the trickiest one. How would I take 1/2 and raise it to an exponent such that I got 16? Well, to flip the fraction, to change that 1/2 into a 2/1, I'd need a negative exponent. and then 2 to the 4th power equals a 16. Put it all together and we get -4. Both pieces there. Way to go. So -4. And then lastly, 1/3 to the 4th power equals 1/81st. What questions do you have about our logarithms evaluations? So now we're going to add another layer because you guys are good with the power statements, and we're going to go ahead and put x in each of our expressions. When we put x in our expression, depending upon where it is, you'll use a different series of inverse operations to solve. So everybody, let's rewrite first as a power, and then solve for x. I'll go ahead and rewrite the first column, but then you and your partner are going to figure out what x would have to be. So base to the exponent equals input. Base to the exponent equals input. Base to the exponent equals input. Go ahead and complete the remaining statements and solve for x with your partner. Again, depending upon where x is, you use a different series of inverse operations to solve, and you can do these through inspection or your power sheet. So rewrite it as a power first, and then use your knowledge of powers to figure out what x would have to be. Again, you can do this with your partner, and I will call on people to share. And you can do all 10. I just wrote the power statements for the first 5.
Yeah, no, not. Yeah, oh, so wait. Yes. So take one. If you like doing one. They would.
Oh, I see. You're just doing the equations. Okay.
That's what I just.
Yeah. My bad.
No, it's okay.
Okay, ladies and gentlemen, it's that time where we're going to share our responses. Depending upon where x was, you could get it through inspection, right, using your powers hack sheet. Let's go ahead and check our answers. Be ready to share with the class when I call on you. So in the first one, x cubed equals 64. What would x have to be? So what did you get for that, Isaiah? 4. 4 is correct. Raise your hand if you get the same. 4. Good job. What would number 2 be? Number 2 then would be Cameron? 1/4. Nice job. Raise your hand if you had 1/4 for the next one. Good job. Then number 3, 5 to the what would equal 625? Courtney?
4.
5 to the 4th. Raise your hand if you had 4 for number 3. Good job, you guys. You're doing great. And so 4 to the x. This is the tricky one. To make a fraction, we need what kind of exponent? a negative exponent, and then raised to the third power. So put it all together, -3. Only positive base b's are allowed, and so while the equation x squared equals 81 has two solutions, 9 and -9, we're only going to have positive base b's in our logarithms, just like for our exponentials. And so we're only taking the 9, only taking the positive 9. 4 to the fourth power equals 256. 1/27 is 3 to the -3rd. 4 to the -1/2 is 1 over 4 to the positive 1/2. That's the same as 1 over the square root of 4, and that's 1/2. So 1/2 is number 8. 6 squared is 36. And then lastly, the trickiest one, in my opinion, was that 100 to -1.5. We could treat that -1.5 as a fraction, and then I'd have 100 to the -3/2 is what x equals. And a negative exponent doesn't mean negative answer, it means reciprocal. So I could rewrite this one more time as 1 over 100 to the +3/2. And I know that the fractional exponent, I can purposely apply the denominator as a root first, so this would be the square root of 100 is 10. And then 10 cubed is 1,000. All underneath 1 is 1/1000. Let's check. Survey says, ding, 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 1/1000. And so 1/1000 is the last one, and that's the trickiest. What questions do you guys have about our logarithmic form? Let's do one more graph, nail down a vertical asymptote versus horizontal asymptote, and then we'll have closure. We'll get you guys some work time while you're still in class. And so let's do one more graph. Let's do, starting out with a logarithmic function. Recall, ladies and gentlemen, that a logarithmic function is an inverse of an exponential function with the same base. And so if I were going to rewrite y equals log base 2 of x in exponential form, it would be base to the exponent equals input. This would be 2 to the y equals x. And by rewriting it like this, it might be easier to get points x comma y, not by choosing x values like we did in our first example, but by choosing y values, because it's easy to evaluate that power. So I would encourage you to choose y values like -2, -1, 0, 1, and 2 as a means for generating points x comma y on my original function, because it's easier for us to evaluate an exponential form than a logarithmic form since they're still brand new. So once again, let's go ahead and choose y values instead of x values after rewriting exponential form, and now evaluate to get points on my original graph. Here we go. 2 to the -2 equals the what x coordinate? Well, that's 1 over 2 to the +2. That's 1 over 2 squared is 1/4. 2 to the -1 equals what x coordinate? Well, that would be 1 over 2 to the first is 1/2. 2 to the 0 is 1. 2 to the first is 2. And 2 squared is 4. Everybody to match colors, I'm going to go ahead and plot that original. Y equals log base 2 of x in blue. So 1/4 comma -2. 1/2 comma -1. 1 comma 0. 2 comma 1. And 4 comma 2. Let's carefully connect those in the xy coordinate plane and extend that, and we'll get a logarithmic function. A logarithmic function has a vertical asymptote. A vertical asymptote has an x equals equation, in this case x equals 0. In fact, this function does not exist for 0 or negative input values x. And so it only exists on the right half of the graph. This is what we call a vertical asymptote. And that's your last homework question involves asymptotes. So vertical asymptote, we've seen that with our hyperbola functions and our inverse squaring functions. So our vertical asymptote at x equals 0. Now let's go ahead and invert. Let's invert my x and y, and I want to get 2 to the x equals y, or y equals 2 to the x. Y equals 2 to the x is an exponential function. I can evaluate that by plugging in x values -2, -1, 0, 1, or 2. But I also know they're inverses, and so I could simply invert the ordered pairs in my original logarithmic function with the corresponding base to get integer pairs on my new function, the exponential function with base 2. So let's go ahead and do that. If 1/4 negative 2 is on the original, then negative 2 comma 1/4 is on the exponential. 1/2 comma negative 1 corresponds to negative 1 comma 1/2. Go ahead and complete the inverses. 0, 1, 1, 2, 2, 4. Let's carefully plot my green exponential function. Ready? Negative 2 comma 1/4. Negative 1 comma 1/2. 0, 1, 1, 2, 2, 4. Whoa, look how steep that gets. My exponential growth function gets steep very quickly. My exponential function has a horizontal asymptote. A horizontal asymptote, the y values get closer and closer to y equals 0, but never get there. So it's like a shelf. The exponential function sits on top of, I'll go ahead and add that as a dashed line. So my exponential function 2 to the x has a horizontal asymptote. And the equation of a horizontal line is a y equals number, right? A y equals number. In this case, y equals 0. And I'm going to go ahead and add that dividing line in. That's pretty sweet. Awesome. Let's go ahead and sum it up with our closure then. So I want you to go ahead and rewrite this exponential statement, w to the p equals m, as a logarithm. Please write the logarithmic statement, log base h of y equals n, as an exponential. Tell me how the graphs of y equals log base 5 of x compares with the graph of y equals 5 to the x. And lastly, what circumstances, what word or words would authorize the use of e in growth or decay situations? You may check with your partner and then be ready to share on the whiteboard. Okay, go ahead and share with the class the logarithmic form in number 1. So rewriting that exponential w to the p equals m in logarithmic form would look like what? What would that look like? Go ahead and share with the class. Virginia?
Log w m equals p.
Log base w of m equals p. Raise your hand if you have the same as Virginia. Log base w of m equals p. Good job. A logarithm is an exponent, and so the overall log must equal the exponent. The base on my logarithm is the same as the base of my exponential, right? And then there's my input. So log base w of m equals p. Nice job. Rewrite as a power statement. Number 2, go ahead and share with the class. Olivia T.
H to the power of n.
Raise your hand if you had the same as Olivia. H to the n equals y. Good. Base to the exponent equals input, because a logarithm is an exponent. And so that's my exponent. H to the n equals input y. Nice job. How do the graphs of those functions compare? So how does y equals log base 5 of x compare with the graph of y equals 5 to the x? Jimmy?
They're the same.
Let's go ahead and take a look at log base 2 of x. How did that compare with 2 to the x? Just like log base 5 of x comparing with 5 to the x. So how do those graphs compare?
They're inverses.
Absolutely, they're inverses. So graphically, how do they compare?
They're reflection over x or y equals x.
Absolutely, and that's what we're after. So yes, they're inverses, but how do they compare graphically? Then they're mirror images. They're reflections of one another about the line y equals x. Good, thank you. And lastly, what word or words authorizes the use of that number e in growth or decay situations? So what word are we looking for in order to allow us to use the exponential growth or decay equation? Like, what's that word that we're looking for? What's that word we're looking for? Matab? Continuously, absolutely. So anytime we're saying that a quantity, right, grows continuously, right, continuously, compounded interest, or decays continuously, then we're talking about using Euler's number in my equation. E is a number so famous it gets its own letter, continuously. Did I spell that right? I back up, does it look better? Awesome. Great job, you guys. I'm going to go ahead and stop the recording now, and we'll see how Ethan's guest appearance in today's recording affects the number of likes on our YouTube channel. And so thank you for that. And let's go ahead and get going right away